This is an attempt to teach Kruskal's minimum spanning tree. So I'm trying to solve that. I'm trying to teach that by solving this lead code problem 1584, minimum cost to connect all points. Okay, so let me try reading the question. So you're given an array points representing integer coordinates of some points on a 2D plane. Okay, the points are given with x and y coordinates. Uh, so the cost of connecting 2 points is the Manhattan distance between them. So this is the Manhattan distance between them, uh, which is absolute value of difference between the x coordinates and difference between the y coordinates. Okay, so we have to return the minimum cost to make all points connected, which means that we have to apply a minimum spanning tree algorithm here. Okay, so all the points are connected. All points are connected if there is exactly one simple path between any 2 points. Okay, which states the same thing. We have to solve this with minimum spanning tree. Okay, so this is one of the examples given here. Um, Consider these points here. So let us consider this to be 0, 1, 2, 3, and 4. So 0, 0 is 0, 2, 2 is 1, 3, 10 is 3, uh, 5, 2 is 2, and 7, 0 is 4. Okay, so we have to have a way to connect all of these. It could be something like this. Okay, this is also valid. Okay, um, so there shouldn't be a cyclic connection. If if I join these both, then it will form a cyclic connection, right? So that shouldn't happen. It should be a tree. It should not be a graph. Okay. So let me try solving this using Kruskal's minimum spanning tree. Okay. So let us identify these points by their indices 0, 1, 2, 3, and 4. 0, 1, 3, 10 is 2, 3, and 4, right? So first of all, I'll have to find out Manhattan distance between each of these. So it is like Manhattan distance between 0 and 1 is 4, and Manhattan distance between 0 and 2 is 13. Manhattan distance between 0 and 3 is 7, and so on. Okay, these are all calculated. I have pre-computed all of these, and this is what it is. Okay, so I have actually sorted them. Uh, So if I sort them by Manhattan distance, this is how it looks. Okay, so let us try to apply Kruskal's minimum spanning tree algorithm. The algorithm is quite simple. You'll have to know uh, union find to actually implement this, but I'll try to explain that here as well. So first of all, let us consider a representative. We have 4 vertices here. Okay, so let us have a representative array which is 0, 1, 2, 3, 4. We have exactly 5 vertices here, which are represented by 0, 1, 2, 3, 4. The indices of them, as explained here. Uh, so the indices are 0, 1, 2, 3, 4. Okay. So 0 is represented by 0, 1 is represented by 1, and so on. Okay. And let us have a size array because there are 5 vertices here. We'll have 5 sizes equal to 1. Okay. All of them are independent. None of them are connected so far. Okay. So uh, right now, what we do is we have sorted this particular Manhattan distance between each and every vertices, I mean every 2 vertices by the Manhattan distance, right? So the minimum Manhattan distance is this one, 3. Okay, so we have to go with this. Okay, so a connection between 1 and 3 will cost us 4. Okay, the Manhattan distance between them is 4. Okay, the cost of connecting 2 points xi uh, yi, xj, yj is the Manhattan distance between them, which is this, right? Uh, so cost of connecting 1 and 3 is 3. Sorry, it's not 4, it is 3. Okay. Uh, so this is 3, right? So now what we'll do is we'll have to connect 1 and 3. This is 1 and this is 3, and the cost is 3. Okay. Next, so how do we connect it? So first of all, before connecting, we'll have to check the representative of 1. Okay, the representative of 1 is 1, and the representative of 3 is 3. The size of 1 is 1. The size of 3 is 1. When we have 2 vertices with the same size, the union of them. So any of them can represent the other one. Okay, so every single time we have both of them of same size, let us consider the one that is to the right to be representing the left one. Okay, so if 3 has to represent 1 here, okay, so what happens is okay, 1 is also represented by 3. Okay, and the size of 3 is right now 2. Okay, now we have 3 and 4, right? A connection between 3 and 4 has a Manhattan distance of 4, which means the cost is 4. Okay, so right now in the previous iteration, so let us consider a solution initially to be 0, right? When we've connected nodes, vertices 1 and 3, the Manhattan distance between them is 3, and that is the cost, right? So we'll have to add that cost. So far the cost incurred is 3. Okay, now 3 and 4 are the next nodes. Okay, 3 is represented by 3 itself, and 4 is represented by 4 itself. So they are two independent nodes, independent vertices, and the cost of 3 is 2, and the cost of 4 is 1. So 3 has a higher cost here. Okay, so 4 will also be represented by 3. Okay, so 4 will be represented by 3, and the cost of 4 will now become 3. Okay, so because 4 is the Manhattan distance, and we have made a union of uh, two different vertices here, we'll have to add that. Okay, now let us go with the next one. Okay, the next one is 0, 1, and the Manhattan distance is 4. Okay, the distance, so 0 and 1 are the vertices here, and the Manhattan distance is 4. 0 is represented by 0 itself, but 1 is represented by 3. Okay, because 1 is represented by 3, we'll have to go here and check the size for that. So the size of 1 is 3. Okay, I forgot to actually add this. So this is 3 and 4 with a cost of 4. Okay, so 1 is actually represented by 3, and the size of 3 is 1, 3, and 4. Size is 3. Okay, so now that the size is higher of 1, we'll have to represent 0 as well with 3. Okay, so if we represent 0 as well with 3, what happens is 0 will be represented by 3, and the size of this particular 3 will become 4. Okay, now let us try adding 0, 4. Okay, 0, 4, and the Manhattan distance is 4. Oh, 7, sorry. Okay, okay, so 0 is represented by 3 and 4 is represented by 3. Both of them are represented by the same vertex here. So when both of them are represented by the same vertex, I forgot to add this again, 0 and 1 are connected with a cost of 4. Okay, so 0 and 1, 0 and 4 are represented by 3. Both of them are represented by the same one, which means that it is already connected. When it is already connected, we will not have to do anything else. We'll just have to skip that. Okay, let's go with the next one. 1 and 4. Okay, 1 and 4, and the cost is 7. 1 and 4 are again represented by 3. Okay, this again we'll have to ignore this because both of them are represented by 3. Okay, next 0 and 3. 0 and 3 are both represented by 3. So we'll have to ignore this as well. Okay, so 0 and 3, and the cost is 7, and we'll have to ignore this as well. Okay, and next comes 1 and 2, and the cost is 9. Okay, so 1 is represented by 3 and 2 is represented by itself. So these are two independent vertices, so we'll have to connect them. Okay, the size of 1 is actually represented by 3, so the size of that is 4, and size of 2 is 1. So we can simply, while performing union, right, if we perform a union between 1 and 2 and the cost is 9, so 1 and 2 and the cost is 9, then what happens is 1 will be represented by, sorry, 2 will be represented by the representative of 1, which is 3. Okay, and the size of 3 will be incremented by the size of 2, which is 1. So 4 plus 1 is 5. So all of them are represented by 3 right now, which means they are all connected. And next, whatever we get will be ignored. Okay, And because we have added this cost here, this should also be added. Okay, I actually forgot to add this one. So this was added, this was added, and this was added, and this was added. This was ignored, this was ignored, and this was ignored. Okay, so plus 4, if we calculate this, we'll get a solution of 8 plus 3 plus 9, which is equal to 20. Okay, so if you check in the example given, this is the exact same diagram drawn here. Okay, the cost is 9 for connection between 1 and 2, and the cost between 0 and 1 is 4, and the cost between 3 and 4 is 4, the cost between 1 and 3 is 3. Right, this is the same one. So let us try to implement this via code. Okay, so for this, first we'll have to calculate the Manhattan distance. So let us write a helper function for that. So private int Manhattan distance between the coordinates x2, x2. Okay, this is simply the absolute value of x1 minus x2 plus dot abs of y1 minus y2. Okay, so this is the Manhattan distance. So now we'll have to have a representative to have a union find, right? So representative, I'm just making it a global variable so that it can be accessed outside the function. So representative and size. Okay, so the length of this points array we have is, let us store it in n. Okay, now we have to initialize representative. Representative is equal to new integer of size n, and size is also new integer of size n. Okay, now what we have to do is we have to find out Manhattan distance between each and every point. So for that I'll use two for loops. Okay, and at this point x1 is equal to points of I, y1 is equal to points of I of 1, and this is 0, right? And similarly I'll have to do it for j, y2, j, x2. Okay, so I'll have to store this somewhere. So I can store it in an array, I can store it in a list, or I can store it in a heap queue. Heap. So if I use a heap, it's actually going to be a heap sort if I use a priority queue. Okay, it doesn't matter if I use a priority queue or a simple list, but for now I'm going to use a heap. Okay, so I'll have to add each of this point I and point j and Manhattan distance between. Okay, okay, uh, and then while heap is not empty, okay, get the element from the heap and then apply union. Okay, so let us consider solution is equal to 0 initially, and then solution plus equal to union of this temporary. Okay, so to apply union and find, we'll have to use two variables. Okay, one for find. So how do we find one? If I is represented by itself, then return I. If not, find the representative. Okay, so this is find, and then a union method. Okay, union takes in an integer which will have three values. Okay, so uh, let us consider I is equal to find of the first one, which will be I here, and then j is equal to find of the second one, which will be j here. I actually forgot to do this. I'll have to add a comparator. So I'm adding the Manhattan distance here. So I'll have to compare with the third one. That's the reason I've used 2 here, right? And I'm doing it in. So this will be a min heap here, okay? Okay. If I and j are represented by the same one, then simply return 0, okay? There's nothing we'll have to do for this case. If that's not the case, if size of I is greater than size of j, do something, else do the opposite of it. But whatever be the case, return the Manhattan distance between them in this case. That will be added to the solution, right? That's what we've written here. That will be added to the solution and then return the solution. Okay, so what do we have to do here? So one thing is, if size of I is greater than size of j, then we'll have to acquire the size of j as well into I, and we'll have to do the opposite in the opposite case. Okay, and representative of j will be I. So j will also be represented by I. Okay, this is the opposite case. So here I forgot to actually initialize the representative array. Representative of I is equal to I, and size of I is equal to 1. Okay, so this is fine. So what is the time complexity for this particular algorithm? So we are applying 2 for loops, right? So this will take O of n, and this will take another O of n, right? So it will be O of n square, and then we are adding all that to a heap, and then so this is O of n square until here, and because we are using a heap here, we are actually doing a heap sort, right? And we are doing it for every single element here. So until the heap is empty, we are doing it. So we are applying heap sort on n squared element. Why n squared element here? N is the vertices here, right? So the number of edges we have is about n square. That's why we are applying a heap sort on n squared element, which means that the time complexity of this will be n square into log of n square, right? But we know that log of n square is 2 log n. So this will be equivalent to n square log n. Okay, this will be equivalent to n square log n. And what is the memory we have used? So the space complexity is O of n square, because if we have n vertices here, we'll have about amortized n square edges here. Okay, for each vertex we'll have n minus 1 vertices that we'll have edges we'll have to calculate for, right? So this is the algorithm. Let me check if I've made any compilation errors. No, I haven't made any. Okay, so let me try to okay, this is the program that I've written, right? Yeah. Okay, let me try to submit this. Okay, that's it. It actually showed a little better than this, but this is leetcode. Okay, so that's it. Thank you.